initially we introduce. Okay. So the KVL, KCL, Kirchhoff voltage law and the Kirchhoff current law. How KVL and KCL can be applied for transmission lines and microwave frequency, right? Okay. Initially, the idea is KVL, KCL can be applied to KVL and KCL can be applied to transmission lines or lump element model is valid only when the physical length is much shorter than the wavelength of signal. This is very important assumption. Okay. So then, for transmission line and microwave, how we can apply the KVL and the KCL? We purposely divide the transmission line. Divide the transmission line to very small, very short. Okay, very short transmission line, so that the physical length is much smaller than the wavelength. Then KVL and KCL can be applied, right? So then from there, the wave equation. What is the wave equation? So wave equation, we can produce the wave equation. This is the first order, second order, right? So these two equations are very important, right? Then from there, you can get the solution. The solution voltage is similar to the electric field. Current is similar to the magnetic field. So for the solution, it's incident wave. Actually, it's a combination of incident wave and reflected wave. Right? This is incident. The second item is reflected. Right? Okay. In the meantime, we have introduced some very important parameters like characteristic impedance. Also, this is similar to the intrinsic impedance for our wave, plane wave chapter. Okay. So some other parameters like propagation constant. Then we, for us, we more look at the situation for lossless. Okay. Right. Okay. So this is very classical, very important, very typical circuit. Okay, this the transmission line problem. Right, we introduce the transmission line equation. That equation is a 5-star, 6-star important equation. Right. Okay. Then this is very important problem for us to solve. Right. Very important. 5-star, 6-star important. So here is a transmission line. One end is connected with, for instance, transmitter. Another end is a load, for instance, antenna. Okay? So you can link with a real world problem. Okay? Real world problem. Then you can understand what we are trying to do, right? We are trying to do. Okay, so what we are trying to do, for instance, also we can link with the real world problem. For instance, the base station antenna for silicon application installed at those very tall building, right? You can observe those base station antenna. Actually, link with the base station antenna antenna, there are some transmission lines connected with transmitter. Typically, the transmit power is very high, for instance, 100 watt. Okay, 100 watt. Then we have already addressed those issues. We have already addressed those issues. For instance, the reflection coefficient, right? Okay, reflection coefficient. When we look at the reflection coefficient, means also we have look at the incident power, reflected power, right? Okay, the incident and the reflected power. Reflecting power will be converted to what? Okay. The reflected power will convert to heat. Okay, so cannot be used. Also for transmitter, for instance, for defense application, big antenna array. So actually for those phased array antenna, a small percentage of reflected power need a huge cooling system. So for this system, not only the electric performance, we need those electric performance. Also, we need those how to cool the system. Not antenna itself will not produce the heat. Right? Don't have the thermal issue. However, the antenna will connect with the transmitter like a mobile phone, right? So if you talk with your friend using mobile phone for some time, then okay, so the heat issue will arise. Okay, right? So similarly for phased array antenna or other transmitter receiver, okay, also have similar issues. So how to reduce for real world, how to reduce the reflection is very important. Very important. Now for us, we just learn how to evaluate, right? So for your further module, for instance, level 3, level 4, or for instance, another very popular module, IF communication, right? For E4101E, very popular. Actually, I'm also the lecturer of that module. Okay, so we have more than 60 students, more than 80, even more than 80 students, more than our current students. Also, I'm very surprised how we can help so many students who are interested in our up-level module. Okay, anyway, we try to convey the message. All this can be linked with real-world problem, right? Okay. So currently, what is a typical problem is we need to evaluate how much power will be reflected, right? Okay. What is a reflection coefficient? At this location, maybe a different location. The reason is the reflection coefficient is a complex number. SWR is a real number. Okay? SWR along this transmission line. Since we are only consider the loss leaks situation, along the transmission line, SWR is a constant value. Okay? The reflection coefficient along the transmission line, the magnitude actually is constant magnitude. However, the phase will change from location to location. For instance, here this location load or the generator, those phase are different, right? Okay. So this is, as mentioned, this equation, super important transmission line equation, right? Okay. And this one is the same one, okay? Somewhere this is the transmission line equation or telegraph equation. Okay. So we also have gone through all these two very classical examples. Okay. Now let's move on to another topic. We need to look at then the maximum or minimum of the standing wave, the magnitude, okay? The minimum value or maximum value for the standing wave, okay? Actually, this section is again similar to what we have learned for the plane wave. Quite similar, okay? Quite similar. Okay, now along the transmission line, okay, we have, this is incident, this is reflected. Also be careful, we have mentioned in the transmission line, right? In the transmission line, okay? We have two coordinates. One is z, right? Z, then this is 0. Means the left-hand side is negative, right? Okay, another coordinate is air. For air coordinate system, this is 0. Then the left-hand side is positive. This is negative, right? So here, this is incident. Initially, in terms of z, it's minus jk, right? Okay. Now for this is incident. Although this the sign is positive, right? Okay. So be careful. Now this is total voltage along the transmission line. Includes incident and the reflected, right? Incident and the reflected. Okay, now let's look at the overall voltage. This is the peak value along the transmission for the incident. Okay, so it's incident plus reflected. Now our objective is to try to find the maximum and the minimum. So we use the similar approach. Okay, by using the complex plane. Okay, so for this complex plane, 1 plus gamma, right? 1 plus gamma is incident and reflected, right? Okay, so in this complex plane, so this can be expressed as gamma minus 1. So means the distance from -1 to any location along this this unit circle. Okay, this unit circle, any location, the amplitude or magnitude is the same, right? But the phase will change. Why this phase will change? So in the last slide, we mentioned this is complex. This is complex number, right? Okay? This is a complex number. So here, assume this is magnitude less than 1, right? Okay? This, the magnitude of this definitely is 1, right? Then comes gamma air. Right now, here, this maximum is gamma air, right? Gamma air. So, compare with those in the previous chapter, so we can understand what is the maximum value for the location along this circle and between any point and this point. Okay, so the maximum value must be this point and this point, right? Okay, right? So maximum is 1 plus gamma, right? Okay. now this, okay, the minimum that's here is 1 minus gamma, okay, 1 minus gamma, right? 1 minus gamma. Yes, here, this location is the distance, this is, right, E theta L minus 2 JKL is any location. Then times the gamma L, right? Just now we have this times this, okay? Now, one is at this location, this distance, another this distance, okay, it was maximum and minimum, okay? Maximum corresponding to this is standing wave, right? This is the peak value, maximum, this minimum value, okay, right? Okay, similarly, then we can move. So also similarly, later, you will be asked to find a location for the maximum and the minimum, okay? Since, again, this reflection coefficient is a complex number, okay? This is a complex number. Okay. So to have the maximum value, similar to the previous, okay, to have, just now, to have the maximum value, this should be 2, this cosine alpha, or this should be, this phase, now this is the phase, okay, should be minus 2m pi, right? Okay, similar to those contents in the plane wave chapter, so I will not spend more time on these details. So it turns out the location will be equal to this value, will be equal to this value. So this is the maximum, minimum is, the value is quarter wavelength away from. So the difference is quarter wavelength, okay? Quarter wavelength. So also previously we mentioned this maximum and the minimum, the distance just now we mentioned is lambda over 4. So 2 maximum, the distance is lambda over 2, right? Okay, lambda over 2. 1 period. So here also mentioned, since this is what air increased by lambda experience 2 period, so that's why here is lambda over 2. Anyway, 2 peaks, this distance pi over 2. Okay, so for minimum, we mentioned this. You can write down those equations in your F1 F sheet, right? Okay. Then current. Okay. Actually, when voltage has a maximum, current will have minimum. Or when voltage is at this, for instance, at this location, it's also similar to electric field and magnetic field. For instance, at this location, voltage is maximum on this location. Then current will be minimum. Okay? Current will be minimum. At this location, voltage is minimum, then current is maximum. So it's a same location, at the same location, voltage maximum, at this location, voltage minimum, then current maximum. Okay? Right? This is quite similar to previous case. Then the definition of standing wave ratio, sometimes we call this voltage standing wave ratio. Then it's voltage VSWR. Some different textbooks. Sometimes we use VSWR. Sometimes we just use SWR. Okay? Actually the same. Okay? VSWR or SWR. Okay? SWR. The relationship between SWR and the gamma air, or from standing wave ratio, you can calculate the magnitude of reflection coefficient. These two equations are very important, very important, right? Yeah, Einstein important. Okay. So for some special case, so previously, I guess we have mentioned, for instance, match load. Match load, the load is matched means the reflection coefficient is 0. Reflection coefficient is 0, then from this equation, if the reflection coefficient is 0, then standing wave ratio is 1, right? Okay? If, for another case, if it's a short circuit is reflection coefficient is -1. -1, then this standing wave is infinity, right? It's infinity. Then if it is open circuit, the load impedance, here we means the load is matched or short circuit or open circuit, okay? Then reflection coefficient is +1. +1 again here, standing wave ratio is infinity. Actually, the standing wave ratio range is from +1 to infinity. Okay? Standing wave ratio will not be less than 1. Okay. Now we look at another important topic is power flow. Okay? So just now I mentioned this, we try to link with real work problems. So finally we still need a hand answer those engineering problems. Right? How much power can be transmitted? How much power will be reflected? Then for your further study, we try to minimize the reflected power. Right? Okay? Improve the efficiency. Right? Okay. So this is from the reflection transmission those interface. In the future also for your further study, you for the transmitter, how to improve the transmitter itself efficiency. Just now I just mentioned for those interface, transmission line, then the load, those reflection. Actually more important, yeah, in addition to improve those interface efficiency, also we need to improve the efficiency for the transmitters. For instance, currently, typically those transmitter with linear, for instance, a mobile transmitter. Right? Typically the efficiency only 20%, means 80% of power has been converted to heat, not used. Right? Okay, so how to improve those efficiencies also very important. Very important. Okay, now let's look at the power flow in a transmission line. Again, those contents are very similar to those in the plane wave chapter. Okay, so how to evaluate the power transmission. Okay. Now, time average power flow at any point on a transmission line. So it's given by this, okay? Average power. Okay, be careful here. We have a few definitions. So sometimes we could confuse. The average power, here is the average power. Okay? Is equal to 1/2 real part is the voltage times the current, the commutator. This power what is transmitted in the transmission line. Okay, at this location, the equivalent circuit. So this equivalent circuit is for that, for this, right? This VG, then one section of transmission line, right? One section of this, the air, right? This is one section of transmission line. This transmission line could be very long and could be very short, right? Okay, right? This is one end. Now the eye means looking to the right hand side, looking to the right hand side, right? So in previous sections we have already simplified this transmission line to this, right? We have already simplified. Okay. Actually here, the average power, later I will explain further, okay? So anyway, bear in mind, this is very important. When this is very classical problem, right? Also this can be simplified as this, right? Okay, what is ZI? ZI is impedance looking to the right hand side. Once we have this, then this can be, since we have this is equivalent impedance, right? Then this can be simplified as this, okay, right? Power delivered by the source. Okay, here, some the definition for different power. Okay, this is average power. This is average power. Okay, now this is power delivered by the source. This is the total power generated by the transmitter or the generator. Okay. What is II? Just now we have this, right? We have this VG, VI, right? Okay, this VG, VG, this equivalent, right? II is VG divided by ZG plus VI, right? Okay. Now the power dissipated in the source impedance means the power dissipated on this source impedance, right? Okay, this power is generated by this source, right? This PS. ZG is the power consumed by this source impedance. Definitely we use the same equation, right? You can obtain this. Anyway, all this can be calculated. Once VG, ZG are given, ZI can be calculated, right? Later we have the example. Okay. Now, power input to the transmission line. So this produce the power will consumed by this and this, right? Okay. This is produced, then consumed by this and by this, right? Okay? So now the power input to the transmission line actually is equal to this. Okay, this is the total voltage at this location, This is the current at this location. Okay, anyway, later I will explain further. So, for this power input to the transmission line. Also, you can use this equation or this equation. Notice Zi is the complex number, so cosine theta Vi will be involved. Okay, this is not typical. So power. Okay, there is another definition of power dissipated in the terminal impedance. Terminal impedance. What is terminal impedance? Again, I draw this. This is a transmission line, right? This is a load, okay? The load. This is a source, right? Source. This VG, okay? VG. Load means this, for instance, antenna. Then transmitter link with transmission line to the antenna, then transmit power will be transmit to free space. Okay, so dissipated in the terminal impedance means by this one, then volt here. This is suppose this coordinate, for instance, this L, right? L equal to 0, voltage and current can be calculated. Okay, so anyway, you can use these two, either current or voltage, you can calculate this PL. Okay, so by the principle of conservation of power, just now we mentioned, source power should be the power by the internal impedance, and the power just now we mentioned for the simplified version, right? ZG VI, right? This is so source is equal to this. Now this input power, actually this is lossless transmission line. Okay? Input power is equal to, means input power will be 100% transmit to the load. Okay? To the load. Then you could ask, then how about the reflective power, right? Reflective power. Okay. Actually, sometimes even ourselves will be calculated, right? Input power. Also, we have the incident power and the reflective power. Input power, actually, this PI, later on we will have, okay? I just posed this question, right? Here we should have the reflective power. Where is the reflective power, right? Okay? Then here, the average, we have another, just now we have the average power, actually average power from all this we sell. Actually we can sell this and plug this into this equation, right? This is total voltage along the transmission line, total current along the transmission line, means incident and reflective, right? Incident and reflective. Then we sum into this equation. Turns out we have this, okay? You can sum into this equation. Turns out we have this, Okay, actually this term always is imaginary number. So this is, for instance, this complex number minus the conjugate is the complex number. So the real part of this means this can be dropped, right? This can be dropped. Turns out average power is equal to this. Okay? Is equal to this. Average power along the transmission line. This is, we call, the first item is incident power. The second is reflective power. Incident times the reflective coefficient squared, right? Okay? So now be careful, the incident minus reflector is the average power transmitted along the transmission line. Or Actually, this is PI, or input power. Okay? So some is input power. Input power is equal to the power at the load. Okay? This is input. Input. PI is input, not incident. This is incident. Sometimes we use incident. Okay? Incident minus reflected is input. Okay? So previously, here the I is input. Input. Okay? Input power. Not incident. Right? Input power is the average power. Also, as mentioned, along the transmission line, at this location and this location, the input power, if it is lossless transmission line, the input power is equal to the power absorbed by the load. Absorbed by the load, right? Okay? This is very important. Also, some students could be confused. Yes. Okay, good. Okay, now let's look at one very important example. One very important example. Okay. Now, a lossless transmission line. A lossless transmission line. As mentioned, this is a very classic problem. The characteristic impedance is 50 ohm, right? Okay. Now the distance, this distance D is 1.5 meter. Connect this transmission line, right? Okay. Connect a voltage source to terminal. Okay. This is source, right? Then this load. Okay. Right? So need to read the question properly, okay? The load is a complex number. If the voltage is 60 volt, operating frequency is given. Source impedance also given. Find the distance of the first voltage maximum. Okay? From the load. This is question 1, right? Question 2 is what is the power delivered to the load? Just now we mentioned delivered to the load. You have two approaches to calculate, right? One is to calculate the voltage and the current at the load, right? Then by using the equation, you can calculate the voltage and the current at this load, right? Right? Okay, then use this equation, the real part, VL, IL, calculate, right? Okay, in the meantime, since this is lossless transmission line, actually the load power should be equal to the input power, right? Okay, should be equal to the input power. You can also use this approach to calculate this. Right? Either one should be okay, but this could take more time. Okay, right? Assume the speed of the wave along the transmission line equal to speed of light. What does this mean? This sentence. This sentence means that dielectrical permittivity epsilon R is equal to along this inside this transmission line is equal to 1, right? Is equal to 1. If this speed is less than 1, for instance, is C over 2, for instance, is C over 2, then the relative permittivity epsilon R will be what value? 1249. What is the value of epsilon r? What is the value? Okay, anyway, I will give answer first. Okay. Yes, right? The square root is there. Okay. So for this question, following information is given just now is our characteristic impedance. We can write here the source, right? This VG, then the impedance, then the load, right? This is very classical, okay? Very classical. Vs, Vg, Vl, V0, right? Vl, okay? This is a length, then this D, okay, here is D. Vg is given, Vg is given, load impedance, also complex number. Now, from here, from this, you can calculate the wavelength. Since this is C, means epsilon r is equal to 1. If not equal to 1, here the wavelength need be considered the effect of epsilon r, right? Okay, so reflection coefficient at the load is very straightforward, right? At the load is just, this is very important equation, right? Load, the reflection at the load, right? Okay, very important. Then, just now, the first question is to find out the location to have the maximum, right? Okay, then we just use this equation. So notice now theta L is greater than 1, so A equal to 0 will be chosen. So means theta L lambda divided by pi, this is not difficult. Just apply this, also be careful, right? Apply this equation. So the input impedance, we just use this very important equation. This is the transmission line equation, 5 star, 6 star important, right? Okay? Then this is K, right? KD, okay? Since wavelength K is equal to 2 pi lambda, right? Lambda is 3 meter, okay? So turns out VI is this number, okay? Is this number. Again, then the transmission line can be simplified as this, as mentioned. VG, VI, right? VG and VI. So the current is just voltage divided Vg and Vi, right? Okay? So quickly you can calculate. Also notice that you need to verify. I have emphasized many times. Don't just read. You need to calculate. Okay? You need to write. In the meantime, during your read with your notes. Okay? Try to get the same value. Then the power actually is equal to input power. Real part, this real part is 50 ohm, right? Then it's very straightforward. Input power is equal to the power delivered to this load, right? Of course, you can calculate the voltage and the current at this load to verify whether it is equal to this. Let me check whether we calculate or not. No, we didn't calculate. Okay? K is the propagation constant. Since lambda is here, right? Lambda is here. K is equal to 2 pi over lambda. This is very important parameter, right? Propagation constant, okay? Okay, so you need to make up by yourself, okay? Read through those vector nodes. Anywhere in the plane wave, we also have already explained what the K is, right? K is 5 star, 6 star important parameter. Okay, right? Okay. Then let's look at some special cases of transmission line. Actually, we almost have already explained all those important equations, okay, for the transmission line. Now let's look at some special cases. One is match load. Match load means the load impedance. Load impedance is equal to the characteristic impedance. Means actually no reflection. No reflection. All the wave will be absorbed by the, for instance, antenna, right? Okay, if the load is antenna, then absorb, then transmit to the free space. Actually, for a very important task for engineer, for RF antenna engineer to design a good matching. The antenna is good matching. Okay, at the desired operation frequency. Okay, now if the match means the load impedance is equal to the characteristic impedance of the transmission line. Okay, then if we sum this into this equation, turns out this at any location of the transmission line, for instance, this Z0, this also Z0, right? Yeah. Okay, any location, we don't care about the distance. Okay, actually, we don't care about the distance. At any location, the input impedance should be Z0, right? It should be equal to Z0. Once the load impedance is equal to the characteristic impedance, right? So we don't care about the distance. You can directly write. Actually, you don't need to write this equation. You can write the input impedance is equal to Z0, right? Z0. Also, the reflection coefficient from this equation, at any location, the reflection coefficient is equal to 0. Means all the power will be transmitted or absorbed by the load. So there's no reflection on the match line, only incident voltage. Okay, for this case, we have already mentioned is traveling no reflection, so it's traveling the magnitude for the voltage and the current are constant. Also means SWR should be equal to 1, right? Also, for previously when we mentioned SWR is maximum and the minimum, the ratio. Now it's constant, definitely. Okay? For the voltage or current, the ratio is 1, right? Okay? Right? Another special case is short circuit. Okay? For short circuit, okay, now short circuit, the load, for instance, for the how we can achieve short circuit for real power is actually for instance, the planar transmission line. we just make a hole, then fill with metal. Okay, the transmission line on the top, the bottom is the ground plane. Okay, then at one end we just drill a hole and then connect the transmission line with the ground plane. Then that is short circuit. Okay. For short circuit, the load impedance is zero. So then the input impedance actually for a short distance, okay, this voltage and the current from here actually you can what you can observe is now the impedance for short distance. Now this is similar. This is similar. What? Actually, this is for inductance. For inductance, air. For inductor is actually is J omega air, right? For inductance, if the inductance value is air, then the impedance is J omega air. Then this is similar to this. Okay? So means of short circuit can be equivalent. Short distance less than lambda over 4, then can be considered as an inductor. Means at microwave, you can realize an inductor by using one section of short circuit. The input impedance, if this length, okay, this length less than lambda over 4, then the input impedance is similar to an inductor, okay, similar inductor. You can realize the inductor by using this approach, okay? Means the planar plane or planar transmission line approach, okay? Then open circuit, okay? Transmission line not connected, we just leave open. Then the input impedance, the load, then this, now the load impedance is infinity. Okay? So, then the input impedance actually can be considered as a capacitance. Okay? For capacitor is J on 1 over J omega C, right? 1 over J omega C. So it's similar to this. Means first short distance, okay, means less than lambda over 4. For instance, this lambda over 4. Okay, this below this 0 means it's more capacitance. Okay, then input impedance is more capacitance. Okay. Okay, another very important. Just now we have mentioned the 3 special cases. One case is the metro load, short circuit, open circuit, right? Another very important is quarter wave length. Okay? Quarter wave length, if the length is quarter wave length, this, what is the input impedance? What is input impedance? Then if we look at this, K is 2 pi over lambda, right? Then times lambda over 4. This is the K air, right? As mentioned before, this is the electrical length. Now what is the electrical length of this? It's pi over 2, right? Pi over 2, right? Okay? Pi over 2. Then what is tangent pi over 2? What is this value? Infinity. Then
Also, as mentioned before, since this is infinity, okay, this finite, this can be ignored. This also finite can be ignored, right? Okay? Since then this has been ignored, then this j can be cancelled, right? Turns out this also can be cancelled, okay? Can be cancelled on top and the bottom, right? Okay? Divider, same value, okay? So turns out this input impedance is Z0 times Z0 divided by ZL, okay? By ZL, right? Later I will explain. This is very, very important relationship, okay? We will use this relationship for impedance matching, okay? This is 6-star important relationship. 6-star, okay? Important. Then let's look at another case. Another case is the length. For instance, this length is half wavelength. For half wavelength, then half wavelength, this times lambda divided by 2, right? Half wavelength. This is electric length, Ka, right? Ka. Now is inside is Ka, right? And this is very fundamental, very important transmission multiplication. First, we can calculate the electric length. Now, this is pi. Then tangent pi is equal to 0, right? Okay. Since this is 0, this can be this will be 0, right? Okay. Turns out this will be cancelled. Is equal to ZL. What is ZL? It's load impedance. Means, what does it mean? Okay, initially at this location, the impedance is ZL. Now, after half wavelength, you will see this ZL again. Okay, after half wavelength. Then, for instance, we have another half wavelength. For instance, here is 1 wavelength. Then what is input impedance? Now this length is 1 wavelength. What is input impedance? What is input impedance? What is the input impedance? Okay? Just now we mentioned half wavelength, the input impedance is ZL. Okay? Then another half wavelength. Okay? What is the value? ZL, 2ZL. Any objection? Yes. Is ZL, right? Just now we mentioned the input impedance. Look into the right hand side. If this is lambda over 2, right? Now we don't care about the right hand side. Now this is ZL, right? Then by another half wavelength, of course, here. Again, we repeat is ZL, right? Okay? Okay, now let's okay, let's finish this, then we have a 20 minutes break. Okay. Now, actually this slide, we summarize what we have discussed. We summarize what we have discussed before. For those short circuit, this also summarize those important equations, right? Important equation. Okay? The relationship, the gamma L, SWR, the gamma L from the loader, or reflection coefficient this is transmission line equation. Just now, this beta air is electrical length. Air is a physical length, right? Beta is the propagation constant. Okay? Open circuit match load here for this, for instance. This is also be careful, okay? Also be careful. Here, small z. Small z means this z is the location, right? This small z. Here, z no, this is impedance, right? This is impedance. If load impedance is 0, then sub into this equation, gamma L. We sub into this equation, gamma L is -1. Then sub this equation, SWR is infinity, right? Okay? For match load, then photo wavelengths, later we will explain further. Okay, now let's have 20 minutes break. Okay, 20 minutes break. Okay, also now we should submit your assignment 2. Okay? In the meantime, our TA is here. Lee Wan. Our TA is here. No. Okay. Anyway, she will bring the assignment 1. Okay? For all two. Okay? Now it's time to. Oh, yeah, it's here. Okay? No? Yes. Please cover all the contents. Yes. Next week. Yes.
here. Now it's coming. Okay. Okay. No, don't put at the same place. Okay. You can get back your assignment one. Okay. You can put there.
你懂我这个什么意思吗？我去拿了 MC， 我去学校做了。如果可以，我要先去看医生，拿了 MC 来干什么？因为我要去沙滩，因为那个沙滩的东西我还没有去找，找了之后去第一个去那不是本地哥那边，然后我再去看，然后我再顺便去拿药，讲这课，再去拿上网。我明天差不多下午就下来。到可以 finish everything 的。你的 IC， 我不是你的 IC， 你的 IC 啊，我已经买了，你 transistor 买了，所以我们的那个我们的那个东西对不对？跟他录的东西就可以还给他了，也是potential meter 而已。然后我们一起potential meter的时候，对不对？要 record， 然后 after that 我们就这样回去我买了之后，知道给他。因为这个 because I need this spot for the use lah for my to use that's my business. Then from there 啦，如果这个东西是成功的话，对不对？apply power 成功的话啦 then the next step is 会 connect 这个 oscilloscope to 我的 PLC， 我再去做那个，我去做那个 PWM 那个是爬步可以做完，如果听完爬步可以做完到爬步的时候，对，那个还是看可以到10嘛 ，H break 我只是要修的东西而已。我们的东西 first part 是要做 breadboard 成功了之后，对不对？把它把它transfer 去vertiboard 成了，对不对？那个东西是 connection 不够。这个盘对，我会放一些 output point output test point 放在那边，改次对不对？我的 customer 来的时候啦，我做这个把 project 给 professor， 我没办法一点意思。
他怎么解释花了一点背心？最多差1块钱。